Historians believe that the Maya civilization began approximately 1000 BC. However, most of the Maya achievements occurred during the Classic period, from approximately AD 250 to 900. It was during this time that Maya civilization flourished. The Maya built dozens of cities, excelled in architecture and astronomy, and developed a complex culture centered on commerce, farming, and religious beliefs. Unfortunately, most documentation of ancient Maya history has been lost or destroyed. When the Spanish entered the Yucatan Peninsula in the early 1500s, Maya culture had already begun to decline. The great Maya cities had been abandoned for more than 600 years, but the Maya had built new cities elsewhere. The Spanish entered these cities and conquered their residents. Very little survived this period, and much of what we know about Maya writing, calendars, and arithmetic comes from a small number of documents and from inscriptions on stone monuments in their abandoned cities. At first glance, Maya numbers don't look very complicated at all. A series of dots and bars, they appear to be basic and primitive. But don't be fooled by the simplicity of these symbols. The Maya created a number system that is as sophisticated and complex as our own. To understand how the Maya did math, it is important to look at our own system first. The numbers we use today are called Hindu Arabic numerals. These numbers originated in India, but it wasn't until they made it to the Arab people in North Africa that they were transformed into the symbols that we use today. We recognize these symbols as the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. All numbers can be written by using a combination of these 10 symbols. Even exotic numbers like pi can be written using these 10 digits. This differs from other mathematical systems. Let's take a look at Roman numerals. In the Roman numbering system, different symbols are assigned to different quantities as they get larger. Between 1 and 1000 are 7 different symbols. The problem with this system is that as numbers get larger, new symbols must be invented. This makes writing large numbers difficult because so many new symbols need to be memorized. The Maya only needed 3 symbols to express any quantity. These symbols are a dot, which represents 1, a bar, which represents 5, and a shell, which represents 0. Rather than writing their numbers from left to right, as we do, the Maya wrote their numbers from top to bottom. Every 5 dots are equal to 1 bar. Let's count from 0 to 10 using Maya numerals. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That the Maya had invented a symbol for 0 is probably the most important aspect of their mathematical system. You may wonder what is so important about the number 0. To answer that question, let's take a look at our Hindu Arabic system again. When we write down numbers, we rely on place value. This means that the value of a number is determined by the place in which it appears. In the base 10 numbering system, we write numbers in increasing order from right to left. For example, in the number 25, the number 5 is in the ones place and 2 is in the tens place. Now let's take a look at the number 205. The number 5 is in the ones place and the 2 is in the hundredths place, but a 0 is in the tens place. This is because nothing is in the tens place. If we didn't have the 0 to fill that space, we would have no way to distinguish between the number 25 and the number 205. Without the 0, place value could not exist. This idea of place value applies to the Maya number system, along with the concept of 0. But the Maya used a vigesimal system, or base 20. This means that each place is equal to a power of 20. In our system, each place is equal to a power of 10. Many scholars believe that our system was designed as base 10 simply because 10 equals the number of our fingers. Scholars also believe that the Maya chose a base 20 system because 20 is equal to the combined total of fingers and toes. And while we write our numbers with increasing place value from right to left, the Maya wrote their numbers to show increasing place value from bottom to top. But place value in a base 20 system has some interesting properties. Let's compare 25 in base 10 and 25 in base 20. You'd think those would be identical numbers, but don't let appearances deceive you. Let's look first at the differences from the point of view of place value. In base 10, the 5 is in the ones place, and the 2 is in the tens place. In base 20, the 5 is in the ones place, but the 2 is in the twenties place. To see how this affects the value of the number, we'll need to see these numbers in expanded notation. In a base 10 system, every number can be written as a power of 10. For example, the number 9,999 in expanded notation is written this way: 9 times 1,000 plus 9 times 100 plus 9 times 10 plus 9 times 1. Expressing 1,000, 100, 10, and 1 as powers of 10, we get 9 times 10 to the third plus 9 times 10 to the second plus 9 times 10 to the first plus 9 times 10 to the 0. In a base 20 system, every number is written as a power of 20. So starting with a base 20 number, we'll use 9,999. We would write in expanded notation using powers of 20. In doing so, we get 9 times 20 to the third plus 9 times 20 to the second plus 9 times 20 to the first plus 9 times 20 to the 0. Simplified, this becomes 9 times 8,000 plus 9 times 400 plus 9 times 20 plus 9, which can be rewritten as 72,000 plus 3,600 plus 180 plus 9, or 75,789. So 9,999 in base 20 is equal to 75,789 in base 10. Now that we've seen the differences and important similarities between the two number systems, let's start using the Maya system of numeration. This number is written in the Maya notation, and since it is on the bottom, it is in the ones place. As many as 19 items can be in the ones place of a base 20 system. Let's count the number. Counting the bars, there are 5, 10, 15 items, and then counting the dots, we get to the number 19. Adding one more dot gives a total of 4 bars, or 20 items. But the ones place can only hold 19 items, so this means we go to the twenties place and put a dot there. The dot in this place is equal to 20 to the first power, or 20. Because the ones place is now empty, we use the symbol for 0 to fill it. Otherwise, there would be no way to distinguish between the numbers 1 and 20. So now we can see how place value works in the Maya system. Each dot in the ones place is worth 20 to the 0 power, or 1. Each dot in the twenties place is worth 20 to the first power, or 20. And because 5 dots are equal to 1 bar, each bar in that place is worth 5 times 20, or 100. As we move up the place value ladder, 1 dot is worth 20 times the value of a dot in the lower place value. The value of a dot in the third place is 20 squared, or 400. And a bar in that place is worth 5 times 400, or 2,000. Let's simplify things again and take a look at the number 25 in Maya numerals. To help distinguish each place value more clearly, we have separated them with boxes. First, look at the bottom box, or the ones place. Remember that 5 dots are equal to 1 bar. So we can determine that the bar written in the ones place is equal to 5 times 1, or 5. Now take a look at the dot in the twenties place. Because this is a base 20 system, each dot in this place is equal to 20 to the first power, or 20. Reading from top to bottom, we add up each place as 20 plus 5, or 25. A dot in each new place is worth 20 times the value of a dot in the previous place. And a bar is always equal to 5 dots. So reading from bottom to top, a dot in the ones place is worth 1, and a bar is worth 5. In the 20s place, a dot is worth 20 to the first, or 20, and a bar is worth 20 times 5, or 100. In the 400s place, a dot is worth 20 to the second, or 400, and a bar is worth 400 times 5, or 2,000. And in the 8,000s place, a dot is worth 20 to the third, or 8,000, and a bar is worth 8,000 times 5, or 40,000.